A palestra é Highrise Buildings Worldwide. Profissional Engineer, New York Fatih Yalniz. Fatih Yalniz tem sido responsável pela implementação de projetos conceituais inovadores para diversos arranha-céus e estruturas especiais. Ele possui ampla experiência em projetos de vento, sísmicos e de controle de vibrações, além de estar envolvido no gerenciamento de projetos e no design de vários edifícios altos e super altos. Ele liderou análises computacionais tridimensionais e o projeto de sistemas laterais para diversos empreendimentos, incluindo residenciais, comerciais, de hospitalidade, institucionais, educacionais e de estruturas especiais. Com vocês, nosso convidado internacional de Nova York, Fatih. Please.
My presentation is basically today just try to give you a few brief techniques and thinking process what we do throughout the design process of a tall building or super tall building. Myself, I'm a structural engineer more than 25 years. 20 years of it is in New York, specialized in tall and super tall building and special structures. I also director of the analysis group, specialized specifically for tall, super tall buildings. These are a few of the projects that I'm involved with, as World Trade Center, Shard 217 West 57, which is the tallest residential building in the Western Hemisphere today. Next one is the MoMA Tower. The other one is the middle one is the middle one is 56 Leonard, also known as Jenga Tower. Next one is American Copper Buildings. These two towers connected to each other with a bridge. The other one is full concrete 432 Park. The time it was built, it was the tallest residential building. 157 West 57th Street. It's also, the time it was built, it was the tallest residential building, and it was the first installation of tall buildings, super tall buildings in the 57th Street line, which is known as a Billionaire's Row. And the last one is 111 West 57th Street. Is as today is the most slender building, the slenderness ratio of 0.24. So the main question is why we do tall and slender buildings. Everywhere in the world, wherever you go, tall and slender building, the reason of tall and slender building is the land scarcity, premium locations, like locations like Manhattan, which is an island. You cannot build everywhere. There's a limited area. Also, city regulations, it means that there are certain zoning areas that you cannot build residential or you cannot build office buildings. So this is all contribute to go taller and higher anywhere in the world. This is included here. Brief description of a slender building. Slenderness is basically a simple ratio of width to height ratio. It's a very important ratio. There are some certain codes, including New York City code, call out buildings when their slenderness ratio is bigger than 1 to 7. It requires additional requirements to do with engineering, additional like alternative load pack or key element and design requirement, just because the building is slender. This is also a very important concept for structural engineers. Although the building may not be too tall, too high, slenderness ratio is high. It also requires significant amount of structure and additional requirements that you have to consider during the construction. So basically, if you think that slender and super slender building based on the different codes has different requirements, different callouts, generally we started to pay attention more than 1 to 7. 1 to 10 is being done a lot of times for the last 10, 15 years. and 1 to 12 starting with 432 Park, and the other tall and super tall buildings is ended up with a 1 to 24, 111 West 57th Street. Graph of the buildings that's showing the height and standards ratio as started in the last 10-15 years. Majority of these buildings are from New York. We started with 1 to 12, and you can see the height is increasing. There are certain buildings 1 to 12, 1 to 12, 1 to 15. Sena Tower is today, the standards ratio is more than 1 to 20. We're not releasing the final height today. And with this height, you will see the real standards ratio of the building. And 157, West 57 is today is the most standard building, 1 to 24, with a height of 434 meters, with a 14 meter width. Sena Tower and comparison from 11th century. So we basically follow the same design philosophy for all our buildings. The first thing that we do is we make sure that all our buildings are safe, sound. We follow the existing code. Sometimes when the existing code doesn't address some issues when we have to a super tall building, we go beyond the code and we have our own codes basically around standards. We have our limitations that we follow, because the majority of the code says today in America doesn't address tall and super tall buildings. The second important point when you design a building is tall and standard building is adequacy of service response. What it means is basically when you're building, you finish a building and it's a residential or office building, the building has to function. So it's not a monument, it's not a statue, it's a building, it's a functioning project. People live in there, people go to work in there. So you make sure that any event, including any wind event or seismic event, the building performs as is designed for. You have elevators always working. You don't have any sound issues. You don't have any tracking noises or any other noises that any other issues that building can stop the users enjoy the building. So, especially residential buildings, we have more restricted criteria that we try to follow, and we make sure that every tall and super tall building have these criteria after the safety. And third one is maximize utilization of the available space. These are, at the end of the day, a building is a product. The product must be a good product. So what you try to do as an engineer, you try to provide the best outcome of the project, the best layout of the project. Make sure that number of the structural elements in the project is limited. So it makes your life easier. It makes it more buildable. And at the end of the day, if it's more buildable, it's a more successful project. And efficiency of construction is the last one. Whenever we design a structure, we make sure that it's buildable. It's buildable with the available materials. It's buildable in a manageable time. You cannot build a building in 10 years. For example, in New York, we generally, in concrete buildings, we pour a floor every 2 days. Here is, I think, it's like 3 times that length. So we make sure that when you design a building that high, 100, 150 stories high, is buildable in a manageable time. You try to make your design simple as possible so people understand it, people know how to build it, and try to do a repetitive design. That's very important. So people get used to it. After a while, after 20 stories, 30 stories, 40 stories, once the construction crew understand that how they build it, it's just starting to cut in the time. So what has been done here is we start with the tests. We look at the materials, we look at the constructability. In addition to that, we look at the serviceability, secondary system applications, and monitoring here. This is the steps that we take in looking in the steps in Senate Tower and the other tall buildings here. Tests, what we did started a step and said, we did some pile tests. We tried to understand what the pile test looks like, what is the capacity. We also look at the concrete. We want to make sure that what is the expected concrete performance. We look at the MOU of the concrete, which is very important for the stiffness of a concrete building. We look at where you can get a concrete, good concrete, consistent concrete, and how much it's going to cost. Is it too far? Is it too close? Do we have to import any materials? So we look at all these details, and we had collected all the data, so we know what we can get any other quarry in here, what we can get in construction concrete plant in Cambria, so understand what we can build, what we should expect. Next stage is constructability. Again, we try to make everything simple. We try to show everything is constructible, not to separate what is being done here. So people have some level of understanding. So they're not getting surprised, because you cannot build the same type of a building in New York and here and expect the same kind of performance from the crew and from the quality perspective. So we make sure that constructability will not be an issue. And one thing about the constructability is it's very important that if you start introducing a number of the structural elements in a building, you ended up with less structure. Once you have less structure, it automatically makes it a more constructible project. You also look at the serviceability within sway measures. It's very important when you have a tall building. Again, it's not very well addressed how the building is going to sway, your elevator is going to work out, because these are extreme buildings. These are extreme structures. It's not everyday structure, so you make sure that all the tolerances, especially plumbing tolerances and sway tolerances, are already being considered before you start the structure. So you ended up with a normal performing elevators, normal performing services, because 150 stories high building, you're not gonna tell the people take the stairs, so they have to take the elevator. And they have to take the elevator in a manageable time. They cannot wait half an hour in an elevator. All these elevators, all these construction issues, serviceability issues are always considered ahead of time. So we design the building, make sure that in any wind event, how the elevators are going to be performed, how much it's going to take them, any passenger from one floor to the next floor, how long it's going to take them. So we make sure that it's a comfortable luxury building that performs very well in any wind event, expected wind event. The other thing is secondary systems. Secondary systems are basically, these are passive dampers. The one on the left is specifically done for Senate Tower. It's 2 QMS dampers. For the last close to 15 years, we installed personally, the projects are working and installed close to 12 of them here in the United States mainly. They perform very well. We have a lot of data. These are tailored machines done for project specific, like it's done for Senate Tower. And we have great experience with them, great experience with the design team, great experience with the installers. So these are very machines to control only for serviceability issues. We're not using them for strength issues, for safety issues. We don't use them. We just use them for control the acceleration, human comfort. These are all passive systems. So it means that they don't require additional energy, outside energy to get activated. The one on the right is a slush tank. That's also an option, not for this project, but for different projects. As a secondary system, it's also commonly used in smaller scale buildings when you need a smaller level of damping, additional damping to control the accelerations. But these are all both examples of the systems, passive systems that we use a lot, and they're all proven systems where they work very nicely. with a proven track record. And the last thing is monitoring. Monitoring is very important because as a structural engineer, as a team, everyone makes some assumptions, and at the end of the day, your secondary system and your building performs based on the assumptions that you make. And at some point, you have to see if your assumptions are correct, how correct they are, how far you are, and if there's a difference, why does that difference happens, what went wrong or what went better than you expected. These are part of the systems that we look at, like the test, pile test, where we know that what kind of foundations, what we're going to get from the foundations. We also look at the concrete. These are all connected to each other because at the end of the day, the secondary system is going to perform what is designed for. If your design is far from the reality, the system is not going to perform. So that's also, we have been monitoring the systems because we've been installing these systems for the last 10, 15 years, a lot. And so far it went well. We are around 5% different than what we assumed in the structural models and fundamental models. But it's a very important part of the process. And we know that it's not being done here a lot, but there's a team in Toll Solutions. They are doing this for 24 hours. They're monitoring the building, existing buildings, different heights, different locations, and they're comparing the structural models and also the wind data that we're getting. So they can produce this information just to understand what was assumed, what is in there in reality for deflections, accelerations. This is one of the projects they did. The information shows that it's close to 5% of what is assumed and what is going to be up in the field. But it's a very important part of the project. So, Senate. So Senate Tower is, I'm not, Stephanie spoke about this a lot. I'm just going to go through the structural portion of it. So Senate Tower, the time it will be finished. It will be the tallest residential building in the world, hopefully. And it's one of the highest buildings. It's just the one big difference about Senate Tower and the other tower is just pure residential building. It's not a mixed-use building. The structure is we have a main spine, we have a main core go through the building, and we have multiple outriggers connecting the outside columns to the core in the mechanical floors to increase the stiffness and control deflection. By doing that, by connecting the central core to the outside columns, we also not reducing the sellable area for residential buildings. We're just using the existing required mechanical areas. But when we decide the mechanical areas, rotations, we always coordinate with the architectural team and the mechanical team, make sure that these are the right locations. But generally, a structural engineer don't decide where this is going to be. This is always a coordination issue. These are all residential floors, below is garage and a few retail stores. These are the mechanical floors, and these are the mechanical floors that we bank on them. At the top, we have a lot of amenity floors. We also have viewing floors at the top of the building, and we have a steel crown at the top. That is housing BMU. And also, it's not fully cladded. It's partially cladded. It's open, porous, to allow the wind to pass. And below that, at the last concrete level, we have a damper. The damper that shows tube mass damper. So structural system, as I said, we have the main core going from the bottom to the top, and we have multiple outrigger floors stated that the mechanical floors connected to the outside columns. This is a typical outrigger floor. And this is a small video of the damper, how it moves. And we have two of them parallel to each other just to control the acceleration of the building at the top is residential floor, top occupied floor of the building, mainly. This is a little bit detail. This is one of the options that the team is considering, the shape. It gives you the understanding is how big is this mission. And at the top, we have the BMU. It's a building maintenance unit, and we heliport at the top. We constantly on purpose, leave the top still open for us to let the wind blow, to reduce the wind impact on the building. We also did extensive wind analysis. This is the wind tunnel test picture. And this is, as a matter of fact, half of the building because the scale is big, so it won't feature the wind tunnel. So this is cut, but this is basically done for the cladding tests. So at the top of the building for the floors. And this is one of the tests that we did. We did multiple tests through the design of the building to see what kind of porosity we can have with the architectural team and with the ownership. Try to take the benefit of having multiple or at least few wind floors to reduce the vortexes on the building. These are other options. With this option at the top, you see we have in this one, we have 3 different wind floors. The ones in the bottom is smallest, and we try to put the wind floors close to the top, and it's more effective. Is another option. So we test all these options, and as today, as Stefan shows in the video, that was the final option that the team decided, the ownership decided, architectural team ownership. And as an engineer, we obliged. Yes, so this is another wind tunnel video. And at the end of the day, we look at the different, we look at how the damper is going to perform. We know that the damper is going to perform. This is not exactly this job specific. This is just a general acceleration graph to just show you what we're looking at, at least what kind of return period. So one thing that we did is as a part of this project is aeroelastic optimization. So we know for a fact that if you chamfer the corners or if you differentiate, it helps reduce the wind effect in the building. This is all known studies. This is another project this was done for a project 1. It's a shape study, and it tells you what happens if the different porosity, different height porosity, different open floors, what kind of impact that you have. When you have a tall and slender building, you do these studies if you can. The architectural team and the ownership allows you to. It's an option. This greatly benefits your structure. The worst shape that you can have is a rectangle or a square, right? Once you start to round them up, you take the benefit of it. If you cannot do it, you start to put, which we did in 3 buildings in New York. Is 433 Park is the first one, 111 Place 57th Street, and Brooklyn Tower. We have multiple porous floors situated right above the mechanical floors. Let the wind go. That reduces accelerations close to 40% in certain buildings without doing a damper. This is a great impact on the building because what you're doing is basically you are disrupting the vortexes in the building. And vortex shedding is that's what you're gonna most probably gonna commonly see in a tall and super tall building. So there are certain things that you can do in the design phase with the design team, the ownership, architect. You can shape the building a little bit better. Maybe sometimes you can rotate the building to just make sure that you get the right wing angles. Or if you have 2 structures next to each other sharing a podium, and you own of these 2 structures, the location of these 2 buildings are also important too. They can have a different impact on each other. So these are the things that you try to look at it when you design phase, all the stage in the building. These are all known facts. If you have a round, you have less wind. And this is one of the buildings that I work with. We have 5 open floors on this one. This is the first one that we did. Then after that, we put that same concept in 2 other buildings. And but the tallest one, residential building in the Western Hemisphere, 217 S57, doesn't have one because the ownership didn't agree. It doesn't have one, it's just solid throughout. So it has to be coordinated with the design team. The other concept I mentioned before is open floor concept. Open floor concept allows, if you have a lot of structural elements, Because it's not good for the construction. It needs a lot of requirements, a lot of coordination issues with the other trades like mechanical and architectural team, and doesn't give you a successful project because if it's an open floor plan, you can do duplexes, you can do triplexes, you can divide them into 3 apartments, 2 apartments. That's what we saw, that's what our experience in the international markets, especially in New York. So we try to have an open floor concept just to help the client to understand that they have options. They can do good structure with more and more openness. This is from 4032 part, and you see that. One thing that we started implying, and this is one of the projects. One, there is open crown. That's what we did in Santa Tower. This is what is decided by the design team. So the whole crown has this material, and it has allowed a certain level of porosity, which allowed the whole wind go through. And it reduced the streaming twice to 25%. So it impacts the foundation, it impacts the structural elements, it eliminates the need of a damper just because the last 20 meters of the building has more porosity. And this is not only one study, they look at the different type of elements and how it's going to look like from far to understand this. And that's what the team decided is for the project one. The second item is open floor concept. The one on the left is just original concept of a floor plan. On the right is updated floor plan. As you see, all the structures pushed to the facade, so the interior is empty. So it allows the ownership, if they want to divide 4 apartments to 3 apartments or 2 apartments, it allows the ownership to sell the 1 floor to an owner. It allows the architect to do whatever they want to do. Mechanical engineers, they can punch anywhere, they can put a stair anywhere. So it gives the project team an opportunity to have a successful project. Structural system is another project, is also a concept, hopefully we can start soon. So in this one, you see that the core is eccentric on the one side, it's a rectangle building, but the structural element sizes and the number of the structural elements are relatively low. It's been done by putting strategically outrigger and belt floors in certain floors to stiffen up. Also in this project, wherever it is required, there are 3 sizes of concrete strength. The concrete strength of the project is not the same from bottom to top. It was done in a way, wherever it is required, the high concrete strength to stiffen the building is the high concrete strength. And as soon as that zone is passed, the concrete strength immediately reduced. So it also saves money and increases constructability. One more thing is the team on the same project, what they do is they assign a different concrete strength for the slabs than the vertical elements because it's really not required. That's the typical application here, but it's really not required. You can have a similar concrete strength than in the slabs than the columns. So it's also another level of saving without any additional requirements. These are the belt floors that we said. So these are amenity spaces, Lazar spaces. So the whole team just pushed these floors a little bit higher and put belts just to transfer the force from the core to the outside elements. So the whole thing is, although the core is eccentric in this building, it is a stiff core, and these are the belt elements to control the deflection. But again, the biggest thing is the shape. Also, the belt, the laser, and all these floors below act like a transfer structure because the garage floors and the above the layouts are not the same. Sometimes, and a lot of times, you have to transfer your walls, columns. You have to add columns. So in order to avoid that, everything is just picked up at the right below the laser to accommodate the layout in the garage floors. And this is another study, which is at this stage is a study. So this building is special because it has a slenderness ratio 1 to 31 right now, and it's here, as you see, a typical shape. It's a rectangle shape, and it has transfers at the garage balance. So how the structure is done is, again, multiple floors. There are outriggers. On top of it, there are 2 open floor concepts just to reduce the wind impact on the building. In this study, it was shown that the wind tunnels showed that adding 2 open floors in this building reduced the wind effect close to 25% with the acceleration. So it's close to eliminating the damper. Even if you put a damper in the building and you have 4 more sellable floors, or you can put 4 open floors, and you're close to eliminate the damper, or at least reduce the requirement from additional damping from a damper. These are a few isometric tower shapes. You see that how standard is that in the smaller direction. And it's close to 100 stories now. And these are, you just manage it with like 4 outrigger floors, also the mechanical floors, and it houses water tanks. There's fire and water. So that's it. So thank you very much for your time.